asymptotic condition. So you see, what I want to point about this condition is that just knowing that you have a solution with finite energy, already you can look at its ends, and it's going to pick up the periodic orbits. You don't have to put them in. They come out sort of as a result of the fact that you have a solution to the equation. Though you cooked up your equation in such a way that, you detect that. So it's not fair to say it this way. And then the other thing I should mention, of course, is that if you look at the equation, there it is, it's invariant under time translation, where time now is this S direction. It's invariant under translation in the R direction. Let me call it R, let me call it S direction. Let me not call it time, because I used to call it T time. Now we have like two different times, so let's not get confused. So it's invariant under translation in S. Okay? And if you remember, whenever you construct a moduli space, you always should quotient by reparametrizations. And so we really should be quotienting by this invariance, by this R translation. So let me say it this way, that the equation star is invariant under the R action. That translates S. This is not, I didn't quite say this the right way, but if I translate S, I get an R action. It's invariant under the action, okay? Maybe that's a better way to say it. And so the moduli space, whichever way you want to decorate it, maybe temporarily I'll decorate it by just its ends. And so we know we have a solution of finite energy. We should also decorate it by the homology class, but let me ignore the homology class for the time being. Let me assume phi 2 is trivial or something like Flirt did. But certainly we should decorate it with the asymptotic ends. So let me say moduli space of solutions going from x plus to x minus. Well, I'll say it this way, x plus minus, so that it will not be so clear if it goes from plus to minus or minus to plus. But anyway, it has two ends. One of them is x plus, one of them is x minus. Okay. So this is the moduli space, is the quotient. By this action. So I hope also I impress on you that when you do these problems, you always should look at things up to equivalence if you want to get something useful out of them. And in particular, the equivalence here is the automorphisms, or if you want, the reparametrization of the domain. Okay. In particular, here they just boil down to translation, because we're really having a fixed cylindrical domain, but that has automorphism, which is a translation. Well, it has also, you could rotate it, but the equation in T, but the equation is not invariant in that. So there will not be an action. I mean, it will be an action, but it will not be automorphism. Okay, all right. And finally, what was the other thing that we needed? So we needed energy. We needed to understand, what happens at the ends, at the punctures, if you want. And we also needed to modify all the automorphisms. The other thing, and we were hoping that for generic parameters, this will be a smooth-oriented compact manifold, right? That we can get invariance out of it. We still need to compactify it. It's yet still not yet compact. So the other thing we need to compactify it. So I'm going to call it m bar of x plus minus. And you shouldn't be too surprised. Maybe you would be surprised. I'm not going to prove anything. I'm just going to say what goes into the compactification. You shouldn't be surprised I'm not proving anything, right? You've been already to several of my lectures. Anyway, but perhaps you shouldn't be too surprised that if you look at the space, if you look at the space of solutions, this holomorphic map cylinders going in a one-parameter family, they're going to degenerate. If you want to compactify them, you'll have to allow them to degenerate. And here there are two really kinds of degenerations. One of them, so the limit, let me say it like that, by adding the limit. And how do the limits look like? Well, you can either have a broken cylinder coming really from broken flow lines. Let me draw the picture. So this cylinder that used to go between two periodic solutions, it may break in the limit and go intermediately through several of them. So originally it was going from x minus, I believe, to x plus. It's going down, right? But it stops, for infinite time. It takes infinite time to get here, and then, and then from here, from somewhere here, it takes infinite time to go here and infinite time to go here. So it's really corresponding to a broken flow line. If if you've ever seen in Morse theory a broken flow line. This is unbroken flow line. Let's say it like that. This is a critical point, this is another critical point. And here's an unbroken flow line. In a one parameter family, this flow line could break and go through an intermediate critical point. And that's really, this process is a good thing because this really comes in proving boundary square equals to 0. You really want this picture to prove boundary square equals to 0. So that's good. This is codimension 1. So these are codimension 1, real codimension 1. Okay, the point to you. This is a property of breaking cylinders plus bubbles, right? So it could also bubble. Remember remote compactness? It could have all these Mickey Mouses bubbles, and the bubbles are holomorphic curves. Plus, so what do you add in the limit? In the limit, you have broken cylinders. And every time it breaks, it's codimension 1 plus actual holomorphic, J holomorphic bubbles. The perturbation goes away when you rescale to get the bubble. Okay? So these are actual holomorphic curves that you get a bubble. And these are codimension 2. Now, you may say, why does she worry so much about codimension 1 or codimension 2? And you may be, it's okay to worry about this. I wasn't very specific before. All the boundary we got in all the other problems that we discussed in the previous lectures were really codimension 2 phenomena, and that was good. Here we have some codimension 1 phenomena, which means that having codimension 1 boundary means basically that m bar x plus minus is at best, so let me say it's generically, let's say it like that, is generically smooth. Maybe let's decorate it like I did before. Generically smooth, right? But it comes out, I mean, again, as I said, under some topological assumptions, it's actually, you can remove the stars. So, okay. Let's leave the stars, but anyway, it's just like before. With enough conditions, generically, it's a smooth, compact. Oriented is okay. Manifold. But unfortunately with boundary and corners. Well, unfortunately or fortunately, it depends on your perspective. From my perspective, unfortunately, with boundary and corners, okay, that's the new feature, okay? It really has its codimension 1 strata, so if you want to draw a picture of the moduli space, well, it looks a lot like that picture, it's a manifold with boundary and corners. It has boundary and has corners, okay? And so, the bad news, if it's a manifold with boundary and corner, is that really you cannot extract an invariant like its homology class, like we were doing in the first lectures. But the good news is, because it has boundary and corners, you can define Floer theory and extract another kind of invariant. Okay, so really, the Floer theory is coming from the boundary structure of this manifold. This codimension 1 boundary is really what makes Floer theory work. And you extract this information in the form of Floer theory. All right, so let me see, I think I didn't want to say more than that. Yes, one more other thing. So remember, it's generically smooth, compact, oriented manifold. Okay, with boundary and corners, okay, now we can live with that, right? We made peace with it. But remember what was the other property we wanted? We wanted to be finite dimensional, and its dimension to be topological, right? So it's finite dimensional, for sure, and its dimension is still topological, so that's the good news. I'm not going to write down the formula for the dimension, but just like before, it involves the very same quantities. It involves the dimension of the target, it involves, the genus of the domain, it's a cylinder, the number of mark points, well, we don't really have mark points unless you think of the ends as being punctures. So it just basically involves the dimension of the target. Let's see, losing anything, yes, it involves the dimension of the target, so that the relative homology class this thing represents, which say, we even kill that. But the other thing that was entering there was the first Chern class, right? So the only thing that changes is the first Chern class. So dimension is still topological, just like before. But the only thing is that the first Chern class, C1, remember we used to have a C1 of Tx, right? Evaluated in the homology class. This term is replaced by what's called the Conley-Zehnder index, by the Conley-Zehnder index of the periodic solution. In this sense, I mean there are two, but like an index of the periodic solutions. Okay, and I did not define the first Chern class, right? So maybe I won't define the Conley-Zehnder index. But let me just say it's a way, it's still something that I would consider topological. It measures, if you go around the periodic orbit, it measures, roughly speaking, how many times the flow rotates around it. Okay, so that's roughly speaking one measure. How much the flow, as you go around the periodic orbit, how much the nearby flow lines rotate. Okay, so that's roughly one measure. So it's something still topological. Okay? And so with this package, then the usual machinery kicks in. And you get, let's see. 15 minutes, thank you. Thank you. Thank you. So just from the moduli space of solutions to this equation, you then get, you study its boundary, and it's really by studying its boundary that you get that this boundary square in the Floer theory equals to 0. So from this, just from these properties, you get Floer theory, and you get it is an invariant. It's well defined and invariant. You have to check, of course, but is well defined. Independent of choices. So invariant. Maybe I'll stop here with this part of the Floer theory, but just to impress on you, really the fact that this Floer theory is well defined and independent of choices comes from the structure of this moduli space of solutions to this particular equation, and in particular its boundary, the way the boundary looks like. And that's related to how the boundary operator looks like as well, okay, and the asymptotic conditions. Okay, so that ends this version of Floer theory, and as I said, there are many different other versions of Floer theory. There is a whole zoo of Floer theory. You probably know and heard many of them. I'm not going to be at all comprehensive. Perhaps also not comprehensive either, but this is the very basic. This one is called Hamiltonian Floer theory. There is a version of it where you let the n be infinite, and of course put some boundary conditions on the kind of n you allow, what kind of manifold X you are allowing, and what kind of n you have. And you get, for example, that way you get symplectic homology. This is what Lisa was talking about, I think, in one of her lectures. Perhaps she was getting it using generating functions, but there's a version of it using holomorphic curves, going along the same ideas. And then there is another version, just to mention. So this was the Lagrangian Floer theory. Sorry, this was the Hamiltonian Floer theory. That you, for example, you can use to prove the first unknown conjecture. Is it still here? Yes, it's here. For the first time, I managed not to erase something important. So this is what you use to prove this unknown conjecture. And then there is another version. Let me just very briefly mention, and that is Lagrangian Floer theory. But there are other things, they're like Hegar Floer theory, Suter Floer homology. Well, homology. Anyway, there are many Rapp Floer theories, many different adjectives, and they all boil down to, roughly speaking, the same idea of doing more. I can come back to say what they come down to, But the other main version of Floer's theory, again, back to going to Floer's and Floer's idea, and I showed you how the finding the periodic solution was the same as finding fixed point of the flow. And there was the same as finding the intersection between the graph of the time one map and the diagonal, which were two Lagrangians. There is this other version of Arnold conjecture involving Lagrangian intersections, right?